So bonding SL, if you want to add on here, this is topic 4. And then when we get to the HL stuff, it'll be topic 14. Okay. So if you hear me say topic 4/14, I'm talking about bonding. Okay. So the beginning of this, there's a recap of stuff that we learned last year. The Octet Rule, which if you guys remember from last year, means that all of the atoms, they want to receive enough atoms that they, or sorry, enough electrons that they have a full outer shell. So for most or almost all of our elements, that's going to be 8. And so that's why it is the octet rule, because octet, it would be a term that it's a group of 8, just like a duet would be 2 or a trio would be 3. So the reason that most of them are 8 is because that is what a stable outer shell would have. There are a couple exceptions. Helium and hydrogen only will have 2, but everything else is going to be 8. Okay, and the reason for hydrogen and helium are only 2 is because they only have that first energy level, and remember that can only hold a maximum of 2 electrons. So we're going to talk about this in terms of valence electrons, but we're also going to talk about it in terms of electron configurations, because what this means is if I look at the outer shell of like this neon and this argon atom right here, I can count and I can see that there are 8 electrons on that outer shell. But what that means in terms of electron configurations, for example, like neon would be 1s2, 2s2, 2p6. That's neon right here. And so if it's going to be a full octet, it's going to have, it's going to end in something s2, something p6. So like neon ends in 2s2, 2p6, because those 8 electrons on those superscripts, that's the 8 valence electrons in the highest energy level. For argon, argon is going to end in 3s2, 3p6, because you can see on this picture that its valence shell is the 3rd energy level. Okay. And so the reason that we call this the octet rule is because the noble gases, they come like this. All of their outer shells are full. And so the noble gases are stable. That's why they don't react with anything. Typically, there's a couple exceptions that we'll get to later in the HL stuff. But for the most part, they don't react with anything. And so they're considered stable because they don't need to gain or lose any electrons. All of the other elements do need to gain or lose electrons. And so that's why our chemical bonds form. They're either going to completely transfer electrons, like in the ionic bonds we're going to talk about today, or the covalent bonds that we're going to get into more on Thursday. They're not going to give away or take electrons, they're going to share them. Okay. And so atoms can achieve, or they can look like a noble gas in terms of its electron configuration by doing one of the things that I just mentioned, by either sharing electrons and making a covalent bond, or by losing or gaining electrons and forming an ionic bond. And so those are our 2 main types of bonds that we're going to focus on in this topic, is ionic bonding and covalent bonding. So we're going to have some stuff that's going to be a recap of stuff you learned last year, just sort of how the bonds formed, what types of elements are involved, and how do I recognize them, that kind of stuff. And then we're going to get into some more detailed stuff that's more for IB, where we're going to talk about how do we know some of the properties of ionic bonds or the properties of covalent bonds, and how do we use that information? How is that useful to us? So I mentioned there are some exceptions to the octet rule. Hydrogen and helium are stable with only 2 because that first energy level. The other ones that are mentioned on here are beryllium and boron. Beryllium is stable with only 4 electrons. Boron is good with only 6. And then the other exceptions are ones that can actually have more than 8 electrons. And that's what we get to in the HL material. Those are called expanded octets. And so everything that's in the 3rd period, which remember that's our 3rd row on the periodic table, the 3rd horizontal row, everything there, they can have more than 8 electrons in their outer shells, the nonmetals. Okay. And so what happens is, because they have those weird d orbital electrons that are involved now, they can expand their octets, and they can actually make 5 or 6 bonds. And so sometimes they can have 10 or 12 electrons in their outer shells when they form bonds. So how do I know if something is ionic or covalent? Because before we get into talking about the specifics of ionic bonding and the specifics of covalent bonding, we got to know how to tell the difference. And so there's a couple different ways. If you're looking at a periodic table, generally speaking, your ionic bonds are going to be a metal and a non-metal. So if you know the locations of your metals and nonmetals on the periodic table, separated by that zigzag line, you can predict, oh, well, if it's a metal and a nonmetal, that's going to be ionic. If it's two nonmetals, that's going to be covalent. Okay. There is a more precise way where we do a little bit of a calculation and we use the property of electronegativity. Okay. That's one of our properties we learned about in topic 3 with periodic trends. And we talked about it in period 3 that it's a measure of the attraction of an atom for a bonding pair of electrons, just like it says right here. And so we talked about in topic 3 that it increases across a period due to the nuclear charge increasing. It decreases down a group because your atomic radius is increasing. And so what happens is, and in your data booklet, you have a periodic table that tells you all the electronegativity values for all the elements. And so you can compare the numbers. So if I'm telling you you're going to have a bond between, sulfur and chlorine, okay, you can look up their electronegativity values and you can subtract them. And when you subtract them, the difference you get, whatever range it falls into on here, that's how you know the type of bond, okay? So ionic bonds, because it is a metal and a non-metal, and metals always have really low electronegativities, non-metals have really high electronegativities. The difference for those, it's always going to be really big, greater than 1.8. So when you subtract, if your group difference is 1.8 or higher, that's most likely going to be an ionic bond. Now, remember, ionic also means metal and non-metal. So a lot of times on ionic bonds, you don't really even have to subtract the electronegativity. If you know your elements, one of them is a metal and one's a non-metal, then you already know it's going to be ionic. The one that you use this subtraction thing for more is to tell these two kind of subtypes of covalent bonds. So there's nonpolar covalent and polar covalent. And nonpolar just means that they are sharing the electrons equally. So there's not a pole, and a pole means that one side is going to be more negative or more positive than the other. Okay. And so it's like there's a pole because there's a little bit of a charge going on there. And so for nonpolar covalent, when you subtract the electronegativity difference, it's going to be almost zero. So it's going to be 0 to maybe about 0.4. Okay. So it's really, really small because they're sharing the electrons equally or nearly equally in that nonpolar covalent bond. So we kind of think that was equal. Now, polar covalent, the difference is going to be larger. It's going to be somewhere between 0.5 and about 1.7. And in this one, it's still covalent, so it's still sharing electrons, but because it's polar covalent, they are not sharing equally. That means one atom has a higher electronegativity, and so that atom is pulling or attracting that bonding pair of electrons closer to it in the bond. And what we're going to learn when we're going through this topic is that things that are polar and things that are non-polar, they have very different properties. They participate in different things differently, like solubility, like how they can dissolve or if they don't dissolve, and some other things that we're going to get to when we talk about properties of these different compounds later. And so it's important that we can identify this basic thing of which type of bond it is, because just knowing that type of bond tells us a lot of information about it. Okay. And so ionic is the one where it's give and take. They're not even sharing. Okay. It's totally transferred. All right. And so you can kind of think of it as like almost like a spectrum. And if I were to do draw like a number line like this, and I were to say, okay, here's 0, and here's 0.5, here's 1, here's 1.5, and then we'll make this 2.0, and then it could keep going. Our number line could keep going. But if I wanted to kind of label this, what I would say is I might say, okay, well, from here to here, that is my non-polar covalent area, that 0 to 0.4. Okay. And then the next section from about 0.5 up to 1.7 ish, that is my polar covalent section. That's a pretty big section. Okay. Compared to the non-polar covalent. So a lot of covalent molecules tend to be polar. And then I could have anything above 1.7 where it's 1.8 or higher. Those are going to be, that's going to be my ionic section over here. So it's kind of a continuum. Um, and so sometimes they don't always follow the rules. For the most part, they do follow these numbers, but occasionally they don't. There are some where if you compare them, you'll get less than 1.8, but it's still ionic because it's a metal and a non-metal. Okay, so just be careful. Always look for like metal, non-metal first to identify ionic. And then if you identify that they're both non-metals, then do this subtraction thing to figure out if it's polar or non-polar covalent. Okay, I think our thing is frozen for a second. So ionic bonding, some of the basic things are things that we already learned last year in 10th grade chemistry. Like you guys should know these words, cation and anion. You should know that cations are the positively charged ones because y'all know if you had me last year, y'all know I always make that cheesy joke about that cats have paws. So cations are positively charged. And anions, it kind of looks like the word onion, just with an A at the front. And onions make you cry when you cut them, if you've ever cut them in the kitchen. And that's kind of pretty of a pretty negative feeling. So the thing we need to know here is these associations. So like positive ions or cations, you need to know that they're formed from the metals losing valence electrons. You need to know all of those go together. Positive ion is a cation. That's going to be a metal element, and it's going to have lost valence electrons. And then the anions are all the opposite. They're going to be negative, they're going to be nonmetals, and they're going to have gained electrons. Okay. And so the number of electrons that they need to lose or gain, that depends on the electron configuration, because how many do they need to either lose or gain to get an octet of 8 in their outer shell? Because that's what they're trying to do. They're trying to get that octet rule and follow that. Okay. So what happens is they lose or gain however many they need to, and then they're positively or negatively charged, and then they form what's called an electrostatic attraction. The positive and the negative charges are attracted to each other because opposites attract. And they form these lattice structures where you have kind of alternating positive and negative ions. So ionic bonds don't have molecules. So it's not like we think of the water molecule kind of looking like this. That's covalent. Ionic bonds don't have structures like that. And we're going to talk about what structures they do have here a little bit later on. Another thing in here, you guys have to be able to do the names and formulas of ionic compounds. That's stuff you learned last year. So we're not going to spend a lot of time going over that today. If you need more tutorials on that, you can talk to me and we can kind of work something out. But that's something that was covered last year. And so it is in here for as kind of a review practice, but we're not going to spend a great amount of time on that. Okay. What we're going to focus more on is this second bullet here. You guys have to know the physical properties of the ionic compounds, specifically volatility, electrical conductivity, and solubility, those three, in terms of how their structures are arranged and what that means for them. Okay. And then here it tells you these are the polyatomic ions you should be really familiar with. There's a lot more than of them than this, but these 7 are going to pop up commonly in questions. And so you should be familiar with the formulas and names of these polyatomic ions so that you know what they are when they pop up in questions. Okay. All right. So ion formations. Okay. We talked about neutral atoms. They have equal numbers of protons and electrons. That's why they're neutral. They have no charge. But when you lose electrons, you become positive. That's your cation. When you gain electrons, you become negative. That's your anion. And so this example, this picture, this is a sodium ion. I can see it's Na. It's got a +1 charge because it gained 1 electron. The number on the charge tells you how many electrons that it gained or lost. And if it's a positive charge, they lost them. If it's a negative charge, they gained them. Okay. So, oops, let me erase this. So in this example, sodium is an alkali metal. Okay. It has 1 valence electron in the 3rd energy level. And so what happens is sodium loses that 1 valence electron because if it goes down to the 2nd energy level, that 2nd energy level is already full. It's already got an octet of 8. And so it gives up 1 valence electron, and that 1 valence electron, it goes over here to this chlorine atom, and chlorine is a halogen, which is group 17, and it has 7 valence electrons. And so it only needs to gain 1 more to get to the octet of 8. And so what happens is the 1 valence electron sodium have is given away. It transfers over to the chlorine. So now chlorine's 3rd energy level is full. It's got 8 instead of 7. And so since sodium lost one, it's got a +1 charge. Since chlorine gained one, it's got a -1 charge. And because they're oppositely charged, they attract to each other and form a bond through that electrostatic attraction. Okay, so this is kind of just summarizing what we already talked about, the electrostatic attraction. We want to have a difference of electronegativity greater than 1.8. And the higher the number, the more ionic it is. So sometimes you might be asked a question like, which of these is the most ionic? If they say something like that, most ionic means that when you subtract the electronegativity difference, which one has the largest difference? So if you were comparing two different, ionic bonds, and one of them, when you subtract it, was 1.9, and the other one was like 2.5, the one that's 2.5, you would say that is more ionic, because the higher the difference, the more ionic your bond is going to be. Okay. And we already talked about their metals and nonmetals. So here's that lattice structure. So the lattice structure, like I said, it's kind of a really orderly grid-like pattern. And so for sodium chloride, each sodium ion is surrounded by 6 chloride ions, and each chloride ion is surrounded by 6 sodium ions. Okay. And so all ionic compounds are solid under standard conditions, which means standard temperature, standard pressure. Okay. So ionic compounds are all solid. Okay. The only way they're not solid is if you either dissolve them in water and make them an aqueous solution, or if you can heat them up high enough that they melt. But they don't do it that very easily. They have very, very high melting points because ionic bonds are the strongest of our bonds. They're a lot stronger than the covalent. And so something like sugar is a covalent bond, salt is an ionic bond. And so salt, you can't really melt on a stove. It just kind of sits there in the pan. It doesn't really do anything. Sugar, though, you can melt sugar in a pan on your stove really easily. That's how you make things like caramel and candy and things like that. All right, so the section on writing and naming, I told you I'm not going to spend a lot of time on this. This is giving you a list of general ions, okay, that you should be familiar with. This is not all of the ions possible. And it's having you practice writing the formulas, okay? And then on the writing the formula section, here is a little recap of how you would do it. You need to cross your charges and make sure that you write the subscripts. If it's a 1, you don't write the subscript. And then make sure that if you have like a 2 and a 4, you have to like reduce it and make it a 1 and a 2, okay? All right, so this I think is the last section. Yeah. Okay, so this is really the new information, because we did names and formulas last year and the basic of what an ionic bond is, but we didn't really talk a lot about the properties and the structures. And so that's kind of what's new here for IB. And so these are the 3 that you are required to be familiar with: electrical conductivity, melting/boiling point, that's the volatility, okay, and solubility. All right. So electrical conductivity, here's the kind of the key thing. Ionic compounds do not conduct electricity when solid. So if you just have like a normal, piece of a cube of table salt, it's not going to conduct electricity, because the ions, they're locked in fixed positions in that lattice structure. And so if they're in fixed positions, they cannot move. And so electricity can't be conducted, because electricity has to have a flow of electrons in order for it to work. They only conduct electricity in 2 situations, okay? They conduct electricity, as I said earlier, if you dissolve them in water. So if they're aqueous, an aqueous solution, so like salt water conducts electricity. Gatorade is something that it's really a salt water. They put sugar in it so it tastes better, but it has electrolytes, because ionic compounds, when you dissolve them in water, they break apart into the negative and positive ions, and those are called electrolytes, those types of solutions. And so they conduct electricity because now the positive and negative ions are moving around in the solution. And so there are charges in order to conduct that electricity. The other situation where they can conduct electricity is if they're molten, meaning you melted them. That one is a lot harder to do, because as I said, the bonds are so strong. You have to melt salt, you have to have a very, very, very high temperature, and that's not really something that can be achieved on like your average stove in your house. Okay. You have to have something a lot hotter than that. So those are the only 2 situations they conduct electricity: molten or dissolved in water and aqueous. Okay. And the reason, as I said, is because the ions break apart and they can carry that electric current instead of being locked in place like when it's a solid like normal. All right, melting and boiling point. I kind of already hinted at this with the whole melting thing that we've already talked about, but ionic compounds have very high melting points and they have even higher boiling points because those ionic bonds, that electrostatic attraction between the positive and negative ions, it's really, really strong. They are highly attracted to each other. They do not want to break apart. And in order to change something from a solid to a liquid and then a liquid to a gas, you have to spread your particles apart because that's what happens when you're changing state of something. And so, for example, sodium chloride table salt, its melting point is 800 degrees Celsius. That's really, really hot. That's not something you're gonna be able to do on a stove, okay? Or even an oven, okay? And so in order to kind of specify one other thing, it says here, the greater the charge and the smaller the ionic radius of the ions, the stronger the electrostatic attraction and the higher the melting point. So if you're trying to compare like which of these bonds would have a higher melting point or a lower melting point, what you want to look at is you want to look at the charges and the radius of the ions involved in the bond, because higher charge and smaller radius is going to have a higher melting point because it's going to have a stronger attraction. Lower charges and bigger radius is going to have a lower attraction and therefore a lower melting point. So you're going to have to look at your charges, and you're also going to have to pay attention to the radius. So you're going to have to know, how does radius trend on that periodic table from topic 3. All right, so the last part today is solubility. So solubility is just the ability for something to dissolve, typically in water, because we know most of our solutions are aqueous. All ionic compounds are soluble in polar solvents, okay? So polar solvents will dissolve ionic compounds because polar solvents have a slight positive and negative charge. So for example, water molecules, like in this picture, okay, water molecules always kind of look like this. They kind of look like Mickey Mouse heads. And so the red is my oxygen, the 2 whites are my hydrogens, and this is a polar molecule because both of the bonds are polar. In water, the side with the hydrogen atoms, it has a partially positive charge, and the side where the oxygen is has a partially negative. Now, it's not a full +1 or a full -1, so that's why on the picture over here, it has this kind of weird looking, almost like a lowercase d or a music note that's kind of fancy looking. And that's the symbol we use to indicate that it's a partial charge. It's not a full like +1 or positive or -1 charge. And so what happens is, because polar molecules like water have a side that is slightly positive and a side that is slightly negative, they're able to dissolve ionic compounds because they have that charge. Even though it's not a full charge, it's still a charge. And so what happens is the ions are pulled apart from the lattice structure. And so what would happen is, if I had salt like sodium chloride, this example in this picture, this is showing me the sodium that has been pulled off of the lattice structure from the sodium chloride. And notice that because the sodium is positively charged, all the water molecules are lined up with the oxygen facing inward, because the oxygen side, as I just told you, is the side that's got the partial negative charge. The chlorine, it would look the opposite. If I had the chlorine, I would have my, my chlorine atom, and it's got a -1 charge because it's a chloride ion now. But the water molecules, they would be facing the other way. My 2 hydrogens would be inward and my oxygen would be outward, but they would still surround it. There would still be 6 of them around it, just like the sodium. It would just be, they'd be flipped the opposite way. The Mickey ears would be facing in because the positive side of the hydrogens would be attracted to that negative side of the chloride. Okay. And that's called hydration. And so that's what happens. And when we get into the HL stuff, we're going to talk about, the energy that's involved with hydrating something and that's involved with dissolving something, because there are some things that are involved in breaking apart that lattice structure. It's called lattice enthalpy or lattice energy. And then there's energy involved with actually hydrating. That's hydration energy for something to actually turn into a solution. All right. So you guys have your exercise questions here. And so Does anybody have any questions about any of the exercise questions that you've already maybe started working on that you want to talk about? Because we have about 5 more minutes uh, before I will be switching over.